Lower bounds. An obvious question is whether one can significantly improve the bound in theorem 4.6. We will show two simple results that imply that the regret bound is near optimal. See exercise 4.5 for a better lower bound. The first result shows that one cannot hope to get sublinear regret when t is small compared to log n, and the second shows that one cannot hope to achieve regret little o of square root of t even when n equals to 2. Theorem 4.7 consider t which is less than the log based on 2 of n. There exists a stochastic generation of losses such that for any online algorithm R1, we have the expectations of L R1 to the t equals to t over 2 and yet L mean to the t equals to 0. Proof. Consider the following sequence of losses. At time t equals to 1, a random subset of n over 2 actions gets a loss of 0 and the rest gets a loss of 1. At time equals to 2, a random subset of n over 4 of the actions that had loss 0 at time t equals to 1 gets a loss of 0, and the rest, including actions that had a loss of 1 at time 1, gets a loss of 1. This process repeats. At each time step, a random subset of half of the actions that have received loss 0 so far gets a loss of 0, while all the rest gets a loss of 1. Any online algorithm incurs an expected loss of 1/2 at each time step, because at each time step t, the expected fraction of probability mass pi to the t on actions that receive a loss of 0 is at most 1/2. Yet for t less than log 2 of n, there will always be some action with total loss of 0. Theorem 4.8. Consider n equals to 2. There exists a stochastic generation of losses such that for any online algorithm R2, we have the expectations of L R2 to the t minus L mean to the t equals to the omega of square root of t. Proof. At time t, we flip a fair coin and set L to the t equals to z1, which is equals to the open interval between 0 and 1 with probability 1/2, and L to the t equals to z2, which is equals to 1, 0 with probability 1/2. So no, the previous L to the t equals to z1 is 0, 1 with probability 1/2, and the second L to the t equals to z2 is 1, 0 with probability 1/2. For any distribution p to the t, the expected loss at time t is exactly 1/2. Therefore, any online algorithm R2 has expected loss of t over 2. Given a sequence of t such losses with t over 2 plus y losses z1 and t over 2 minus y losses z2, we have t over 2 minus L mean to the t equals to the size of y. It remains to lower bound expectations of the size of y. Note that the probability of y is t choose t over 2 plus y over 2 to the t, which is upper bounded by big O of 1 over square root of t using a Stirling approximation. This implies that with a constant probability, we have the size of y equals to the omega of square root of t, which completes the proof.